4.2 is the linear restoring force. So just expanding on what we talked about in 4.1, the linear restoring force of a situation that is oscillating. So in this example, we have this box or crate or whatever it is sliding back and forth. So it'll slide that way some, it'll slide this way some. This position right here is known as the equilibrium position, where there is no restoring force being applied to the object. If the object was just sitting there stationary, it would not move. However, if we pull the object this way, now it's sitting over here, then there's going to be a restoring force in the direction of equilibrium. It wants to go back there, okay? If we were to push the box in over to here, now it's sitting here, there's going to be a restoring force directed that way. It wants to go back to equilibrium, okay? So the restoring force that we're talking about, F net in the x direction, is equal to negative kx. This comes from back in, was it chapter 8 maybe, where we were talking about springs. This is the same equation. So the k is the stiffness of the spring. Remember that the bigger the k, the stiffer the spring. And then this x, I think we in chapter 8 called it delta x. But here, if we just define the origin as the equilibrium position, then it doesn't make any difference if we call it x or delta x. So we're just going to call it x. We don't have to worry about the delta x, okay? The negative sign just means in the opposite direction of the displacement. So if I displace it in the negative direction, then it would be negative negative, moving us back in the positive direction. If I displace it in the positive direction, then the restoring force would be directed in the negative direction, and that's why the negative sign is there. So it's just saying the opposite of the direction that we went. The object's maximum displacement from equilibrium is the amplitude. You should know this from pre-calculus by now. So we have the equilibrium position right here. If I push it in to this point right here, then that is going to be the maximum displacement in that direction. If I pull it out to this position, this position all the way over here, nope, I was right the first time, this position right here, I put the origin in the wrong spot, sorry, then we're going to have a maximum amplitude right here. Now, the amplitude is measured, this is very important, from the equilibrium position. It is not the trough to the peak. So it is not from here to here. It's just from the equilibrium position out to here. That's your amplitude. And it's the same in both directions. So it's going from negative A to positive A from the equilibrium position if we call the equilibrium position 0. Okay? All right. The graph that's here, we can see that if we push this in and it comes back out, and then it will go back in, come back out, its position is actually a sinusoidal graph. Okay? Which means that this is known as simple harmonic motion then. Okay, so let me continue on, and now we change the orientation of this situation. So we have a spring that's mounted to the ceiling, let's say. There's no weight on it, so this is just the normal resting position of the spring right here, okay? It has a spring constant of K, just like we've been talking about. Now we attach some sort of weight to it, so we have this box or crate or whatever it is. That is going to cause the spring to stretch. This stretch right here that is caused by the weight of the object itself is just the stretched position from its normal equilibrium spot. This becomes the new equilibrium spot right here once we attach the weight to it, okay? So this delta L, the displacement of the stretch in the spring, so how much the spring stretches when we add it, is this formula right here. Delta L equals mg, so the weight of the object, divided by K, the spring constant. That will tell you how much that spring will deflect from its equilibrium normal resting position to its new resting position. So the role of gravity here is actually just going to tell us what the new resting position is, this delta L, okay? So we have the original length of the spring plus the delta L. Now we have our new equilibrium position sitting right here, okay? After that, then the same equation in the y direction as we had in the x direction comes about. So we have F net in the y direction now equals negative ky. It is the same math, okay? We just had to figure out the deflection because of the weight of the box. Okay? All right? So moving on. We also have a pendulum. A pendulum is also simple harmonic motion. So a pendulum is, like by definition, going to be some sort of string or thin bar or something like that with some sort of a bob attached to the end. So like if you think of a grandfather clock, it's that disc. If you think of just a regular pendulum that you swing back and forth, or like a wrecking ball, that's a pendulum. They all produce simple harmonic motion. So we don't need to go through the process of deciding that it's simple harmonic motion or not. It just is, all right? So the net force is in the tangential direction to the motion. So look at, we have our pendulum attached up here. We got the string or bar or whatever that is. Now it's going to swing out. So once it swings out to its maximum distance, then it's going to want to swing back through, and then it's going to turn around, swing back through, and then it's going to turn around, swing back through. So that's where the simple harmonic motion comes from. Now, where's the net force? The force that's restoring us back to the equilibrium position. Okay, so if we look at the free body diagram for the pendulum bob right here, the forces that are acting on it are its weight down, of course, and also the tension in the string or the bob or bar or whatever it is, okay? Now, we can break the weight component like we've been doing into all year long into components, and we would have a y component and an x component. So because this angle right here is the same as that angle right here by parallel lines, we would have the opposite over the hypotenuse. So that means we're going to use sine for the restoring force in the x direction. So that gives us this guy. So it's W, the weight of the bob, sine theta. Okay? Okay. So the net force is in the tangential direction. This is the tangential direction right here, tangent to the direction that it is moving. So F net equals the weight tangential, which is just the weight times sine theta. So negative mg sine theta. Negative because why?
Because it's opposite to the direction.
Opposite to the position that it's in, yeah. So if it's up on the right-hand side of its equilibrium position, then it will be negative. If it's on the left-hand side of its equilibrium position, then it is negative, negative, which makes positive. So that's why the negative sign is there. It's the opposite of the direction that it's currently in. Okay, so now, if the angle is very small, so typically by very small we mean about 10 degrees or less. So if theta is very small, then we can use something called the small angle approximation. The small angle approximation simply says that sine theta is approximately equal to theta itself. Okay, so F net tangential will normally be negative mg sine theta, but with a small angle approximation, then sine theta is approximately equal to theta itself. So that reduces to negative mg just theta. Okay. Now, also remember that theta is equal to the arc length divided by the length of the radius. Okay, so theta equals arc length over L, in this case, is right here. So that's the length of the string. And if that's the case, then we can swap out the theta with S over L, and then we get this equation here. F net is equal to negative mg over L times the arc length. Okay, so it just will depend on the information that they give you. Now, in reality, we're talking about small angles of 10 degrees or less, but the percentage error here that we're off by is actually very small, even if we're at 10 degrees, like less than 1%. If we go all the way to like 45 degrees, we're still only off in our answer by approximately 10%, which is not very significant. So typically, unless the problem otherwise says you have to use the actual thing and you can't use the small angle approximation, we're just going to go ahead and use the small angle approximation the whole time. Okay? All right. So, a ball is hung from a rope making a pendulum. When it is pulled 5 degrees to the side, the restoring force is 1 Newton. What will be the magnitude of the restoring force if the ball is pulled 10 degrees to the side? What did we do that's different?
We doubled.
We doubled the angle. And what does that do to the force then?
I think it just doubles.
It doubles the force, that's right. So what's our answer?
Just 2 newtons.
Yep. This is a linear situation. The spring, the pendulum, they all are linear, which means one variable is proportional to the other. We doubled one, we must double the other. Okay? That's the whole section.